Okay, so what we'd like to do is figure out the mass of the air in this room. We know that the pressure in the room is about 14.5 psia or so. Just rounding it down a little bit from 14.7 since we're not at sea level. The temperature is about 72 degrees Fahrenheit or so. It's a reasonable number. And if you pace off the room, it looks like the dimensions of the room, on the floor at least, are about 25 feet deep and about 30 feet wide. Now the height of the ceiling, to the best of my estimate, is about 10 feet or so. Looks a little less than 12, definitely more than 8. So there's the dimensions of the room. So now we can figure out the volume of the room, just 10 times 30 times 25. So we'd like to know how much mass of air is in the room. Now you might pause the video at this point and take a guess. How much mass do you think is in the room? Is it 5 pounds, 10 pounds, a half a pound, 1,000 pounds? How many pounds of air are in the room, and therefore how much force will be applied to that mass by gravity? So what could we use to figure this out? Well, the ideal gas law would relate pressure, volume, and temperature to mass. So this is the equation we'll use. Since we're looking for the mass in the room, the mass of air in the room, we better solve for it. So mass is equal to PV over RT. By the way, if you're interested in an easy way to measure things, measure distances without a measuring tape, the easy way to do it is to take 2 steps, and each 2 steps or so is about 5 feet. So you just count it easily, and I'll go off the video, but you'll hear me still. So you start off, you take a reasonably sized step. You want it to be not as far as you can, but farther than your normal step. So you just count it off in this way. 1, 2, 3. So every time your right foot goes forward, for example, you count another 5 feet. So, and I think I counted it wrong. I counted 1, 2, 3. It should be 5, 10, 15. So every time your right or your left, whichever one you want to count from, goes forward, and that's 5 more feet or so. So anyway, for our purposes, this will be close enough. We're just trying to get a rough estimate of how much mass is in the room. So we better plug in the pressure, 14.5 psia. Now, you have to be very careful. You must always use units. If you don't use units, you can easily make mistakes. Units help you. They're your friend. I wish that units were taught in algebra class, but they're not. They would make algebra easier, actually. So pressure, 14.5 psia, that's pounds force per square inch. That's not pounds mass, that's pounds force. There's a difference between force and mass. The volume of the room, let's see, 10 times 30 is 300. 300 times 25, I could do it in my head, probably not on the video, so let's see. 25 times 300, 7,500 cubic feet. And immediately you notice that we've got a mismatch in the length unit. Inches and feet aren't obviously the same length, so we'll have to deal with that. Now the gas constant, R for air, that's just a constant. You can look it up if you have your book. Go to the back in the appendix, and you'll find gas constants. Now the appendices are set up with metric and then English, so you'll need the second appendix. And let's see, let me find it, I'll give you a page number. Looks like the page that I'm on is 884, and the gas constant is listed. Now there's actually 2 gas constants in this book. One is in BTUs per pound mass per Rankine. The other one is in PSIA, cubic feet per pound mass per Rankine. You just use whichever one's more convenient. Now in the ideal gas law, the one that's always more convenient is the one with PSIA, cubic feet, pounds mass, and Rankine. That way you don't actually have to perform any calculations or any conversions in the square inches and cubic feet. So let's plug in the gas constant. It's 0.3704, and that is PSIA. Cubic feet per pound mass per Rankine. Takes care of R, the gas constant. Now for the temperature. The temperature is 72 degrees, right? 72 degrees Fahrenheit. Well, will this work out? Well, there's a hint to suggest to you that this will not work out. The Rankine and the Fahrenheit are not the same unit. In fact, to go from Fahrenheit to Rankine, you have to add 459 point something I can never remember. So I just add 460 because it's pretty close. So just add 460, and that will convert the temperature to Rankine. And now the Rankine actually cancels. Now remember, be careful when you're converting temperature units. Sometimes you have to convert, sometimes you don't. When do you have to convert and when don't you? Well, you convert the temperature when the temperature is an actual measure of temperature. When it's a measure in change of temperature, then Rankine and Fahrenheit have the same change. It's like saying an inch change in length is the same whether you start at 0 inches or you start at 10 inches. It doesn't matter. Okay? So anyway, all of our units should cancel nicely. Pounds force per square inch go away, cubic feet go away, and we're just left with pounds mass. The Rankine I've already canceled. So notice the pounds mass is in the denominator of the denominator. And so when we plug in all the numbers, we should just end up with pounds mass in the numerator. So let me plug everything in my calculator. Let's see, quantity 72 and 460 in quantity, and we've got 550, I'm going to round it off, 552 pounds mass of air in this room. That's a decent amount of mass. It may be a little bit surprising that the weight of the air in this room is over 500 pounds. But there you have it.